That is what I have seen in last 2-3 lectures, because I generally go through all the recorded videos. So quality of the recorded videos was not up to the mark. So I am thinking to continue from my office, considering that it will be better here. So please let me know if it is not good. Okay, then I have to see the another alternative. Is it all right? Okay. Okay. So in the last class, we started looking at the directional nature of the uh, radiation heat transfer. Okay. So why the directional nature of the radiation heat transfer is important? Because see, uh, in general, whenever we look at the radiation, we calculate the radiative heat transfer directly by multiplying sigma, which is nothing but the Stefan Boltzmann constant, multiplied by uh, the temperature raised to the power 4 minus the temperature raised to the power 4 for the other body, isn't it? Correct. That is what we usually do. But this equation is not valid for all the cases. This equation is only valid if we are having perfect black bodies, and also this equation is valid when both these bodies are infinitesimally long with respect to each other and parallel to each other. So only in that case this equation is valid, where the net radiative heat transfer is given as sigma into the bracket T1 raised to the power 4 minus T2 raised to the power 4, where T1 and T2 is the individual temperature of the body 1 and body 2. So this equation is valid only if both the bodies are infinitesimally long and parallel to each other, and these are black bodies. Okay, but whenever we look at the real heat transfer, radiative heat transfer, bodies are not always the perfect black bodies, isn't it? Also, they are not infinitesimally long, isn't it? So how much amount of radiation emitted by one body is actually received by the second body is important, or vice versa, isn't it? So when we are having infinitesimally long bodies, in that case all the radiation emitted by body 1 is intercepted by body 2, and in a similar manner all the radiation emitted by body 2 are intercepted by body 1, isn't it? So because of that, that directional nature we don't have to look at. But whenever we are having the real radiative heat transfer uh, systems, there the bodies are not infinitesimally long, and in such cases the directional nature of the radiative heat transfer becomes extremely important. So how much amount of radiation emitted by one body is actually intercepted by a second body, this particular fact is extremely important. Okay, so let us look at the directional nature of the radiative heat transfer. Of course, we have done it in the last class, but I am doing this again in little bit more detail because this is slightly more difficult. And also this part is not taken directly from the book. So this particular part is taken from different books, so that it will become more informative and easy to go through. So if you look at this particular material in the book, it is slightly more complicated there. Okay. So let us take an example here. There are two surfaces. One is the differential surface dA1, and then there is another surface A2. Now, clearly, if you wanted to find out how much amount of radiation emitted by dA1 is intercepted by A2, if you wanted to calculate that, it's not that all the radiation emitted by dA1 will be intercepted by A2, isn't it? So dA1 is going to radiate uh, in all the direction, but only part of that will be intercepted by A2. Okay, so how much amount of radiation emitted by dA1 will be intercepted by A2, that is figured out using a concept of solid angle. Okay, so what is solid angle here? Solid angle is a angle or a area subtended by A2 at dA1. So this is calculated by first creating a hemisphere. So if you create a hemisphere around this DA1 with a unit radius, and the area which is intersected by this hemisphere will be called as a solid angle. So this is nothing but the solid angle subtended by this area A is nothing but the solid angle subtended by A2 at DA1. So the definition given here is the solid angle subtended by area A2 at the differential area DA1 is numerically equal to the area A of the portion of the sphere of unit radius with center at DA1, which is cut out by a conical surface with a vertex at DA1 passing through the perimeter of A2. So what it means is, if you wanted to find out the solid angle subtended by A2 at DA1, what we have to do is we have to first create a sphere of unit radius, and this sphere is going to cut this particular conical portion at this location. Let's say this particular, maybe I'll just give one more line so that you will understand what I'm trying to say here is, just wait. So this is going to be the radius 1. This is going to be the radius 1, r equals to 1. So maybe I'll just write that. So this is r equals to 1. Okay. This is that r equals to 1. All right. Okay. So this solid angle subtended by A2 at DA1 is denoted by omega. Now consider a case. In this particular case, there is a area A2 which is hemispherical shape and which is completely covering DA1. In this case, it doesn't matter whether DA1 we are moving from one place to another along this circular plane which is at the bottom. So in such cases, the solid angle subtended by A2 at DA1 is going to be 2 pi. Let us look at this particular case. Hello, yeah.
Sir, by the definition that we studied, it is an area. So how area is 2 pi?
It is the angle. I am really sorry here. Just wait. That is why the solid angle is measured in a steradian. It's an angle. Okay. It's an angle. Just wait. The definition, what we are saying, the solid angle subtended by area A2 is the area DA1 is numerically equals to the area A of the portion of the sphere. Okay. So it is basically given in terms of the angle, which is nothing but this particular angle. Okay, just wait. This particular angle will be this definition. I will check it one more time, but you are saying is correct. But this particular angle is going to be the solid angle. That is why the unit is steradian. Okay, I will check it out. What is the correct thing? But this angle should be the solid angle. Okay. Okay. Okay, so now let us consider a simple case here. Uh, Again, here we are looking at the differential surface area dA1 and what is the solid angle subtended by a dA, which is nothing but the differential surface area at dA1. So again, in a spherical geometry, if you look at this particular angle is going to be d phi. So this phi is varying between, if you look at this will be the entire plane. So this phi is varying between 0 to 2 pi. Again, there is another angle which is nothing but psi. So this psi is varying between this to this plane. So that is pi by 2. From uh, uh, the spherical geometry here, spherical coordinates, this width is going to be r sine psi d phi, whereas this particular thickness is going to be r d psi. So in this case, the differential solid angle dw subtended by dA when viewed from a point dA1 is given as dA by r square. So that is the distance between these two areas and the surface area dA. dA by r square, that is what the solid angle is given here. So again we can put it here dA, so area dA we can calculate this width into this breadth, so that becomes r square sine psi d phi d psi, and if you put it in this equation, this r square will get cancelled out. dw or d omega is given as sine psi d phi. Okay, so this, what I feel is this might not be exactly correct. So this is not given. This I will check out whether this is area or the angle. Okay. All right. Okay. So there is another concept is a spectral intensity or the intensity of the radiation. So intensity of the radiation is nothing but the radiant flux passing in a specific direction per unit solid angle. Per unit solid angle. So that is denoted as watt per meter square per steradian. Uh, so this is defined as d Eb lambda divided by d omega. This is what the intensity of the radiation. Again, this lambda is used here. So lambda is basically what it means is this intensity is nothing but the spectral intensity. So this is corresponding to a radiation of a particular wavelength. Also, the subscript B is there. So that means this is with respect to a black body. Okay. So Ib lambda is nothing but the spectral intensity of the black body, which is given as d Eb lambda by d omega. So Eb lambda is nothing but the spectral emissive power of a black body, and d omega is the differential solid angle. So we can find out Eb lambda, that is nothing but the spectral emissive power of a black body by rearranging this equation. So what we are going to get from this is Eb lambda is going to be Ib lambda into d omega, and the integral of that with respect to the angles. Okay. So now d omega from the previous slide, d omega is sine psi d phi, that we can put it here. Again, this psi is varying between 0 to pi by 2. That is what we have seen. This is psi is varying between 0 to pi by 2, whereas phi is varying all along this. So that is 0 to 2 pi. So Ib lambda is given as integral 0 to 2 pi and 0 to pi by 2 Ib lambda. So Eb lambda is given as integral 0 to 2 pi integral 0 to pi by 2 Ib lambda sine psi d phi. Okay. So now here this Ib lambda can further be replaced by a spectral intensity in a normal direction. So that varying between 2 pi, 0 to 2 pi. This entire circle it is going to be, isn't it? This is the differential area. If you wanted to find out, with respect to area, we have to integrate, isn't it, with respect to solid angles. So this phi is going to vary between 0 to 2 pi, whereas this psi is going to vary between this and this, isn't it? So that is between 0 and pi by 2. Is it all right?
Okay, sir. Sir, we are only considering hemisphere.
Yes. What you are saying?
Are we considering only hemisphere?
Yes,
Because
in this case, yes, in this case we are considering the hemisphere, because see, in this case, this will be the area emitted in this area, isn't it? In the hemispherical area, correct? So bottom part we are not looking at. Correct, you are right. Okay. So in this case, that is why uh, it is called as hemispherical spectral emissive power, isn't it? See, here we have clearly mentioned this is the hemispherical spectral emissive power. That is why we are considering the angle between 0 to 2 pi and between 0 to pi by 2. Okay. So in this case, this IB lambda, which is nothing but the spectral intensity of the radiation in any direction, can be represented in terms of spectral emissivity in a normal direction. So that is given by this Lambert's law. So we can put it in this particular equation. So IB lambda is replaced by INB lambda cos psi. If you put it here, then this INB lambda, this is constant. So this we can take it out. Also this d phi is varying between 0 to 2 pi, so that also we can take it out. So integral of this d phi is going to be just 2 pi. So we will have 2 pi INB lambda outside of the integral, and the integral remaining part is 0 to pi by 2 sin psi cos psi sin psi d psi. So only the term which are related to psi are remaining in this integral. Okay. So integral between 0 to pi by 2 cos psi sin psi d psi, this integral, if you do it, this comes out to be 1 by 2. So this 2 get cancelled out. So what ultimately we get is EB lambda, which is nothing but the spectral emissive power of a black body is related to the spectral intensity in a normal direction multiplied by pi. Okay. Again, as we are saying that this is a hemispherical spectral emissive power. Okay. Now we wanted to calculate the total emissive power. So clearly in this case the radiation we have looked at for only one wavelength, isn't it? But if you look at the radiations, these has the wavelengths varying from 0 to infinity. So total emissive power is going to be the integral with respect to the wavelength. So that is what is being done here. So EB is given as integral 0 to infinity EB lambda d lambda. So if we do this integral, what we get is pi integral 0 to infinity INB lambda d lambda. So that becomes pi INB. So from this equation, what we can conclude is the total emissive power, total hemispherical emissive power is related to the total intensity of a black body in a normal direction multiplied by pi. Is it all right? Is it all right? Can we go ahead?
yes, sir.
Okay. Now, as I said that, remember in the starting of this class, I said that when we are looking at the radiation, typically we use the equation that sigma into T raised to the power 4, that's it. But we don't consider the directional nature of the radiation into the account, isn't it? So let us do this analysis little bit in a more detail. So consider that there are two differential surface areas dA1 and dA2 separated by a distance L, and dA2 is making an angle of beta 1 with the normal of dA1, and similarly dA1 is making an angle of beta 2 with the normal of dA2. Okay. Now in this particular case, sorry. So in this particular case, the intensity of the black body, both consider both these DA1 and DA2 are the black bodies. So intensity of the black body in this case given as intensity of the radiation IB emitted by DA1 in the direction of DA2. So whatever the intensity of radiation from DA1 in the direction of DA2, that can be given as the intensity of the radiation in a normal direction. So IN into cos beta 1. So this is the angle which this normal is making with DA2. So IN cos beta 1. Correct. Again, this IN, which is nothing but the intensity in a normal direction for a surface 1 DA1, that can be represented in the form of emissive power by pi. That is what we have proven in the last slide, isn't it? So EB by pi is INB, isn't it? So we can replace this IN by EB by pi, and EB is given as emissive power of a black body is given as sigma raised to the power sigma T raised to the power 4 divided by pi cos beta 1. So this is equation number 5. Now, what is the rate of radiation emitted by DA1? Rate of radiation emitted by DA1 is going to be what? It is going to be the intensity of the radiation emitted by DA1 multiplied by the solid angle subtended by DA2 at DA1 into area DA1. That is going to give me the total amount of radiation emitted by DA1 in the direction of DA2. This word is very important, in the direction of DA2. Okay. So in this case, first we have to find out the solid angle. Now what solid angle? The solid angle subtended by DA2 at DA1. These words are very important here. The solid angle subtended by DA2 at DA1, that we have to find out. Okay. Whenever we are looking at how much radiation coming out from DA1 are captured by DA2, the solid angle has to be found out for the second surface DA2 with respect to the first. Okay. So the solid angle dW or d omega subtended by DA2 at DA1 is given as DA2 into cos beta 2 divided by the distance between these two bodies, that is L square. Okay, so we can put it in the equation. So remember, what is the total amount of radiation emitted by DA1 flowing towards DA2? That can be given as solid angle multiplied by the intensity of the radiation and area. So that can be given as IB d omega into DA1. So we can put all the values here. By putting all the values, what we ultimately get is, so DA1 we have taken it here outside. So what we get is cos beta 1 cos beta 2 DA2 divided by pi L square sigma T1 raised to the power 4 DA1. So this bracket term can be represented as DF12. So this DF12 is a differential shape factor or a view factor or a component factor. So what it accounts is, both these bodies DA1 and DA2 are not infinitesimally long, and isn't it? So only the part of the radiation emitted by DA1 are intercepted by DA2, isn't it? So this particular directional nature of the radiation is captured by a factor, and that factor is referred as shape factor, view factor, or a component factor. So if you look at different books, they have used the different names. So in your BK Datta book, it is referred as a view factor. In some other book, you will find that these are referred as a shape factor. In some books, you will find that this is referred as a component factor. So all these three terms are actually the same. Okay. So again, since we are talking about the differential surface area, that is why this shape factor here is represented in a differential form. Okay. Is it all right? So now you can see clearly the rate at which the radiation emitted by DA1 in general, that is given by what? That is given by just sigma T1 raised to the power 4 into DA1, isn't it? But not all that radiation emitted will be intercepted by DA2, isn't it? So how much of that will be intercepted by DA2 is captured by this particular factor DF12. Is it clear to everyone? Hello?
Yes, sir.
So can you see here that why this additional factor is important here, isn't it? Very often when we are uh, calculate the radiation, we only take the Stephen Boltzmann law considering the black body, just sigma into T1 raised to the power 4, isn't it? But that's not actually true. That is true only if all the radiation emitted by the body is intercepted by another body, and that is not always true, and therefore a shape factor comes into the picture. So that is what we are seeing here in a differential with respect to these two differential surface area. Here differential surface shape factor is coming into the picture. Okay, so now in this case what we have done is we have found out the rate at which the radiation emitted by DA1 intercepted by or flowing towards Da2. In a similar manner, we can find out the rate at which the radiation emitted by Da2 which are flowing in the direction of Da1. That also we can find out in a similar manner, and that expression will be obtained as cos beta 1 cos beta 2 Da1 pi L square sigma T2 raised to the power 4 Da2. So this is just from the analogy we have written. We can prove it also. So with the same analogy as what we have used in equation 6, directly the equation number 7 is written here, where this bracket is represented as df21. So this is nothing but the shape factor of surface area 2 with respect to 1. So shape factor of surface area 2 with respect to 1. Okay. Now what is the net radiation transfer, net heat transfer by radiation? The subtraction of these two factors, isn't it? So this is emitting some radiation, this is emitting some radiation, isn't it? And what will be the total radiation between these two bodies? The net rate of heat exchange between these two bodies, the subtraction of these two factors, isn't it? So that is what is being obtained here. So dQ12 is nothing but the differential heat transfer between Da1 and Da2, that is given as sigma into cos beta 1 cos beta 2 Da1 Da2 divided by pi L square T1 raised to the power 4 minus T2 raised to the power 4. So this equation can be represented in terms of both the shape factors, isn't it? We can represent this equation as dF12 sigma T1 raised to power 4 minus T2 raised to power 4 Da1. This is one equation, and similarly if we wanted to represent this equation in terms of Da2, we will have dF21. Remember F12 if we use, then the area multiplied is Da1. If you use F21, then the area multiplied by is Da2. So we get equation number 8. So from this what we can conclude that dF12 into Da1 is same as dF21 Da2. So this is a very important property. This property we are going to use regularly while calculating the shape factors. Okay, so I will give all these properties in a subsequent slide, but just to give you a perspective, I am telling you this now. So this property is very important here. So the shape factor with respect to the second surface, and if we change the area, in that case the corresponding shape factor also changes. That is what it is. Okay. Okay, so far we were looking at the differential heat transfer. We wanted to find out the total heat transfer. So what we have to do is we have to integrate this differential surface area Da1 and Da2 with respect to its total area. So that is what is been done. So total heat transfer Q12 is nothing but the integration of this particular equation with respect to area 1 and area 2, and that is what is been done in equation number 10. So this is the integration with respect to area 1 and area 2. So this is the only factor which is going to change. This is a common factor. So that is taken out, constant factor that is taken out. Okay. So this integral divided by area 1 is defined as F12, and therefore we can write this Q12 as F12 sigma T1 raised to power 4 minus T2 raised to power 4 into A1. Similarly, we can write it in terms of A2. So if this term which is given in the bracket, if you divide it by area A2, in that case it becomes F21, and in that case we have to multiply area A2 in this equation 10. So this equation 10 you can see is represented both in terms of F12 as well as F21. In both the cases the corresponding areas has to be multiplied. Okay, is it all right? There is a simplified case of this particular equation. If we are considering that the area A1 is very small compared to A2, then integration with respect to A1 is not required. We can take it out directly, this dA1 as area A1, and the integral become cos beta 1 cos beta 2 dA2 pi L square. So this integral part which is in the bracket is represented as F12, and the area A1 is taken out as it is. Okay. So this is what we have seen until the last class. This is what we have seen in the until the last class. I have given it little bit in more detail because this is slightly more complicated than what we see in the other topics in the radiation. Okay. Now, as I said that these shape factors have some properties, isn't it? So, and these properties are very important to evaluate these shape factors for different geometries. Okay. So the first property is the shape factors F12 and F21 between two surfaces 1 and 2 are related by a reciprocal relation. So that is what we have seen, isn't it? F12 into A1. So that is nothing but F12 is what? Shape factor of area A1 with respect to area 2 multiplied by area 1 is same as F21 into A2, isn't it? So this reciprocal relation is very important here. Okay. Again, this reciprocal relation becomes, you can simplify this equation little bit. If one of the surface area is completely encapsulating the other, that means the one surface is surround the other surface completely. In that case, the shape factor corresponding to that particular surface area is just 1. For example, A2 is surrounding A1 completely. In that case, F21 is going to be just 1. So we will have F12 we can calculate as just A2 divided by A1. So the ratio of their area will directly give you the shape factor. Okay, is it clear?
Hello, sir.
Yes, please go ahead.
Sir, in the previous slide, can you please explain how we were able to neglect A1? Like, why did
Considering
we say
that
that's
in this
small?
particular slide we are considering that A1 is small, isn't it? So A1 is small means dA1 itself is A1. You get it?
Yes, sir. But sir, why are we considering it as small?
Okay,
How
I'll
do
just
we
do that.
know?
So remember here why we have taken the differential surface area dA1 and dA2. This is a small part of the entire surface area.
Yes,
Okay,
sir.
but if suppose this entire surface area is small and only the small part is present in dA, let's say in a dA1, in that case you don't require to make the integration with respect to dA1 because that itself is the total surface area. You get it?
No, not really, sir.
Not really. Okay. So suppose see in this case I have shown this dA1 and I said this that this dA1 is a differential surface area. So what it means is there is a bigger surface area and part of that is dA1. Is it clear?
Yes, sir.
Okay. Now I am saying that no, we don't have a bigger surface area and where this dA1 is a part. I am saying this dA1 itself is the total surface area.
All right, sir.
So that means when we can do that, when I am saying that dA1 is a very small. In
Hmm.
that case, I can consider this differential surface area dA1 itself as a A1.
Yes, sir.
So I don't need to integrate because that is the total surface area.
But sir, you've taken a special case where you've considered that
Yes,
it's
yes,
really
that is
small.
what I'm saying. So that is the special case. And I
Okay.
have written it also here, isn't it? The above equation, if one area say A1 is small, then the integration is performed over A2 only. Is it all right?
Yes, sir.
Okay. Okay. So now the second property of this shape factor is the value of the shape factor depends only on the geometry. This is very important. Okay. So for whatever the analysis we have done, this shape factor is only dependent on the geometry. It is not dependent on temperature. It is not dependent on wavelength. It is not dependent on any other thing. It is only dependent on geometry. So if we know the geometry of the objects, we can pinpointedly find out the shape factors directly by doing the required algebra. Okay. Okay. So if we know the geometry, we can find out the shape factors for the system, and we can then use it for calculating the radiant heat exchange between the surfaces at any temperature. Okay, is it all right? So the third property is a surface has a shape factor with respect to itself. What it means is, suppose a surface is concave like this. Suppose a surface is concave like this. So the radiation emitted somewhere here will be intercepted by other part in this particular surface itself, isn't it? So somewhere here this radiation will be intercepted by the location here, isn't it? So what it means is, the surface can have the shape factor with respect to itself if the surface is concave. Okay. Since in this case the radiation coming off from one part of the surface is intercepted by another part of the same surface. But if the surfaces are flat or convex like this, so this is a flat surface or convex, in such cases there is no way that the radiation emitted from one part or one location in the surface will be intercepted by another location. So that possibility is not there. So in such cases the shape factor of a surface with respect to itself is 0. So F11 is 0, here F11 is 0, but in this case F11, that is the shape factor of surface area A1 with respect to itself is not 0. It's not 0. Is it clear to all? Is it clear? Yes. Can we go ahead? Am I audible? Hello? Am I audible?
Yes, sir, you're audible. So
Sorry,
could you
sorry.
explain the concavity and convexity in the previous slide? Like how are we supposed to see it?
So this I'm saying just the surface is concave here, isn't it? Remember, this is the concave surface.
Yes, sir.
So radiation emitted from this part, the radiation emitted from this part will be emitted in all the direction, isn't it? So some of the radiation will be intercepted by this part if these are moving in this direction, isn't it?
Right, sir.
But that possibility is ruled out when we are having a flat surface or a convex surface, isn't it? This is a convex surface, isn't it? So in this case, that possibility is ruled out. Whatever the radiation emitted at any part will not be intercepted by its surface at some other location, isn't it?
Right, so but in the statement it says that the shape factor is 1, or we can say it's non-zero, when one surface completely surrounds the other and the other surface is convex. So, sir, in the first one you said it's concave.
What you are saying? Please come again.
Sir, the statement
The
has
shape
been...
factor is 1 if one surface surrounds. So okay. So for example, see, this third statement is we are talking about only individual surface, and the first statement we are talking about two surfaces, two separate surfaces. That is the first difference. Okay. So what we are saying that, for example, if you are having another surface, let's say here, somewhere in between here. So what will happen? All the radiation emitted by that surface mostly will be intercepted by the second surface.
Right, sir.
So the shape factor of this particular surface with respect to the first surface, that means F21 is going to be 1. Remember, here we are talking about F11, that is the shape factor with respect to itself. Here when we are talking about, this is F21, so that is the surface shape factor of a particular surface with respect to other surface, not with respect to itself. Did you get it?
Yes, sir.
So that is the difference. That is why here the shape factor is 1. Here we are not saying that. Here we are saying with respect to itself whether it will have a shape factor or not. Okay. So with respect to it will have a shape factor only if it is concave. If it is convex and a flat surface like this, in that case, it is not going to have a shape factor with respect to itself. In fact, you can put it F11, but that will be equal to 0. Is it all right?
Yes, sir, got it.
Okay. Now, the fourth condition is there are n surfaces which makes up the enclosure. So there are n surfaces which makes up the total enclosure. In such cases, each surface is going to radiate the radiation, and these will be intercepted by all the surfaces, all n-1 surfaces, and including itself, isn't it? So if it is concave, it is going to intercept itself. Also, the remaining n-1 also going to intercept the radiation emitted by that particular surface. So in such cases, the equations are F11, F12, F13, F1n equals to 1. So that means what? The shape factor of a particular surface with respect to itself and with respect to all other remaining surfaces, the summation of that is equals to 1. So F11, F12, F13, F1n, this is what? These are nothing but the shape factor of surface area 1 with respect to itself, with respect to second surface, with respect to third surface, and that goes all the way to with respect to nth surface, and that summation is equals to 1. In a similar manner, we can write down the same equation for surface 2. So that becomes F21 plus F22 plus F23, and that summation goes all the way to F2n, and that is also equals to 1. So all surfaces, all n surfaces, we can write down this expression. Is it all right? So in addition to this equation number 13, the reciprocal relation is also valid. Remember that this equation is valid, and on the top of that, the reciprocal relation which we have seen, equation number 12, with respect to any two surfaces will be valid. So for example, in this case, F11 and F12, these are related by a reciprocal relation. So how the reciprocal relation is going to be in this case? A1 F11, sorry, A1 F12, A1 F12 is given as A2 F21. A1 F12 should be equals to A2 F21. So that is the reciprocal relationship between surface 1 and 2, isn't it? So in addition to equation number 13, the usual reciprocal relations which we have seen in equation number 12, these are also valid. These are also valid. The last condition is the shape factor F12 between two surfaces A1 and A2 is equal to the sum of the shape factors F13 and F14 if two surfaces, two areas A3, A4 together make up the area A2. Okay. So what it is, basically, suppose let's say this A2 is made up of A3 and A4, isn't it? In that case, F12 is given as F13 plus F14. Okay, but reciprocal relation in this case is not directly valid. So if you cannot write F21 same as F31 plus F41. Okay, so that we can validate from here itself in equation number 14. So what is F12? F12 is going to be what? We can write in terms of F21. So F21 in this case is going to be A1 by A2, A2 by A1, F21. A2 by A1, F21. Remember, F12 is what? A1, F12 is same as A2, F21, isn't it? So we can rearrange that, and what we can write this F12 as? F12 we can write as A2 by A1, F21. And similarly, we can write the expression of F13 in terms of F31. So that becomes A3 divided by A1, F31. So we are just using the reciprocal relation here for these individual terms. And F14 can be written as A4 by A1, F41, and this denominator A1 will get cancelled out. So actual relation in a reciprocal form is going to be A2 F21 should be equals to A3 F31 plus A4 F41, and this is not same as this. Therefore, the reciprocal relation directly from equation 14 is not correct. Is it clear to everyone? Hello? Is it clear? Hello? Can we go ahead?
Yes, sir.
Yes, sir.
Okay. So now let us look at how these effect of this directional thing are going to affect the radiative heat transfer. Let's look at that in little bit more detail. So let us assume that we are having three surfaces. So the surface one is a heat source, so that could be a fuel bed or a fuel bed at a boiler at temperature T1. Okay, so this is nothing but a fuel bed of a boiler uh, at a temperature T1, that is heat source. What is heat sink? Heat sink is nothing but the tubes, the water tubes which receive the heat. So these are at temperature T2. So heat sink is nothing but the water tubes at temperature T2. And in the boiler there are refractory walls are there. So refractory walls are nothing but the surface 3, and these are at temperature T3. So additional information given about the refractory walls are whatever the amount of heat is received by this refractory wall, the same is emitted by them, isn't it? So the net rate of heat exchange is 0 if we look at the refractory wall. Okay, so refractory material radiates energy at the same rate at which it receives the energy and attains T3, which is between T1 and T2. Is it all right? So system is clear to everyone? Hello? So there are three surfaces. One surface is a heat source. There is another surface which is as a heat sink. And then the third surface is which is neutral, which is basically whatever the radiation heat is received, the same is emitted by the surface. So there are three black surfaces, and again we are considering that all three surfaces are black surface. Now we wanted to see how the heat transfer between these three surfaces is going to take place. Okay, another simplification which we are looking at here is between the surface 1, 2, 3, there is a vacuum is present, and even if there is a gas is present, that gas is non-participative gas, so it is not participating in the radiation heat transfer. So there is no convection. That is what we are assuming by this. So there is no convection present here. So we are assuming either there is a vacuum, or even if there is a gas is there, that gas is not participating in the radiation. Okay. So the net radiation heat transfer from surface 1 is given as Q1. So net radiation heat transfer from surface 1 is Q1. So Q1 is basically whatever the heat is radiated from the surface 1 is intercepted by surface 2, and the part of that is also intercepted by surface 3. So Q1 is nothing but what? Q12. So that is the net radiation transferred to the surface 2, and the radiation transferred to surface 3 is given as Q13. So Q1 is given as Q12 plus Q13. Is it clear to everyone? Is it all right? Hello?
Yes, sir, it's all right.
Okay. Now Q12 we can write in terms of the emissive powers and the shape factors, isn't it? So Q12 can be written as A1 into F12 EB1 minus EB2. So the amount of heat radiated from the surface, only part of that is flowing in the direction of A2. So how much part of that is flowing in the direction of A2 is accounted using the shape factor F12, isn't it? Correct, multiplied by area A1. So since we are looking at the total rate of radiation, and EB1 is per meter square, isn't it? So we have to multiply the area, isn't it? So that area A1 is multiplied. The area A1 is the area of surface A1, surface 1, and what will be the total radiation? The total radiation gained by the surface 2, that is going to be just EB1 minus EB2, isn't it? Correct. So because this is a source, this is a sink is also going to emit something, but the source is going to emit more. So the difference between these two is going to be the net radiation that is received by the surface 2, isn't it? Okay, so Q12 is given as A1 F12 into EB1 minus EB2, and similarly we can write down the expression for Q13. Q13 is given as A1 F13 EB1 minus EB3. Is it all right? Is it clear to everyone? So we can put this Q12 and Q13 in the equation above. So if you put it, Q1 is given as A1 F12 EB1 minus EB2 plus F13 EB1 minus EB3. Is it clear to everyone? Equation number 16. Can I move to the next?
Yes, sir.
Okay. So similar to Q1, we can now write down the expression for Q2. So Q2 will also be written in a similar manner. Q2 is given as A2 F21 EB2 minus EB1 plus F23 EB2 minus EB3. Remember here the shape factors will be with respect to that particular surface. So in this case we are looking at Q1. So that is with respect to surface 1. So therefore this F12 is going to be the shape factor with respect to surface, shape factor of surface 1 with respect to surface 2. Similarly, F13 is going to be shape factor of surface 1 with respect to surface 2, surface 3. Okay, in a similar manner, Q2 we can write down. So Q2 is given as A2, F21. So now we are talking about the rate of heat transfer from surface 2. So that is again multiplied by its corresponding area A2, and F21 is the corresponding shape factor. When it is transferring heat to the surface 1, then it is becoming EB2 minus EB1. Similarly, if it is transferring to the surface 3, then it becomes EB2 minus EB3 and multiplied by corresponding shape factor F23. Okay. In a similar manner, we can write down the expression for Q3, which is given as A3 F31 EB3 minus EB1. So these are nothing but the difference in the MEC. Sorry, I lost the connection in between. Hello, am I audible?
Yes, sir.
Yes, sir, you're
Now
audible
you are.
now.
So I'm sorry. Okay. So this IIT network seems like it is messing up in the academic area as well. Anyway,
Not really,
okay.
sir. Otherwise, it's completely fine. It just lagged for a second or two.
So there is a lag. Some
No,
lag
sir,
is there.
it's fine. Oh no, sir. It just lagged for 1 second today. Otherwise, in the other classes, it was much more. So definitely, this is better.
This is better than the network at the residence area, isn't it?
Yes.
Okay.
Yes.
So we will continue here only. Okay. Anyway, so let us continue with the same slide again. Okay. So similar to Q1, we can write down the expression for Q2, and Q2 is given as A2 F21 EB2 minus EB1 plus F23 EB2 minus EB3, that is Q2. Similarly, we can write down the expression for Q3. So Q3 is given as A3 F31 EB3 minus EB1 plus F32 EB3 minus EB2. Now again, see, in the starting itself, what we said that the surface 3 is, if you look at the surface 3, whatever the radiation is received by the surface 3, the same is emitted by surface 3. So the net rate of heat transfer to the surface 3 is 0, isn't it? So Q3 is equals to 0. So if we put Q3 equals to 0 in equation number 17, so what we get is A3 F31 EB3 minus EB1 plus F32 EB3 minus EB2, that is equals to 0. So we can rearrange this equation and we can find out the expression for EB3. So EB3 we can find out in terms of EB1 and EB2. So EB3 comes out to be F31 EB1 plus F32 EB2 divided by F31 plus F32. Is it clear to everyone? Is it all right?
Yes, sir.
So again, this EB3, remember this is the MECU power of a third surface, isn't it? So that we can write down in terms of the Stefan-Boltzmann law, isn't it? So this EB3 is given as sigma into T3 raised to the power 4. So T3 we can directly obtain by using equation number 18, where we have taken the sigma on the right hand side and this entire bracket raised to the power 1 by 4. Is it all right? Sorry. So now this expression of this EB3 we can put it in this equation number 17. Remember in equation number 17 Q1 and Q2 we have written. So in this Q1 and Q2 there is a term EB3. So this EB3 we have to replace. Again, since this Q3 is 0, that means what? Q1 should be same as minus Q2. Isn't it? So whatever the net rate of radiation, net rate of heat transfer by radiation, Q1, that should be same as minus Q2 because Q3 is 0. Isn't it? So Q1, Q2, Q1 is equals to minus Q2 and that is given as just A1, F12 EB1 minus EB2 plus F13 EB1 minus EB3, and this EB3 we can replace by this equation number 18. So that is what is been done here. So this EB3 we have replaced by this bracket. Okay. So this becomes F13 EB1 minus F31 EB1 plus F32 EB2 divided by F31 plus F32. So this F31 which is there in the denominator, if you multiply here, so EB1 F31 and that is a minus sign is also there in the numerator. So this factor will get cancelled out. So what you ultimately get is F32 EB1 minus okay, so this first factor will get cancelled out here if you multiply, and the second factor is going to be EB1 into F32, and this EB1 we can take common here. So if you take that common, this first factor, so what we will get is by taking the common here EB1 minus EB2. So EB1 minus EB2, if you take the common, in that case what we are going to get is A1 F12 plus A1 F13 F32 divided by F31 plus F32. So this is just a simplification of this particular equation. If you rearrange this equation and take this EB1 minus EB2 common outside of this particular bracket, what we get is EB1 minus EB2 A1 F12 plus A1 F13 into F32 divided by F31 plus F32. Is it all right? Is it clear to everyone? This is just the rearrangement of the equation. Okay, is it clear this part?
Yes, sir.
Now in this case EB1, EB2 again we can represent in terms of the temperature, isn't it? So EB1 can be given as sigma into T1 raised to the power 4, and similarly EB2 is given as sigma raised to the power sigma into T2 raised to the power 4, isn't it? So if you take write this EB1, EB2 in terms of temperature, what we get is equation number 19. So equation number 19 is the final expression that is going to give us the net rate of heat transfer from Q1 to from Q1. Okay. So again this particular equation 19 can be further simplified. Remember in this particular equation number 19, even though there are these terms are T1, T2, but there are different shape factors are also there. F12 is there, F13, F32, F31, F32. We wanted to represent this entire equation 19 in terms of only F12. Only F12 we wanted to represent. Okay, so that can be done easily. Remember we can use this fourth property. This fourth property we can use intelligently. So what this fourth property is saying, summation of the individual shape factors for n surfaces, that is going to be equals to 1. So we can write that fourth property here as F11 plus F12 plus F13 is equals to 1, and F11 and F22 both are equals to 0, because we are assuming that these surfaces are flat surfaces. These are not concave. These are not concave, these are flat surfaces, and if you are assuming that these are flat surfaces, F11 and F22 these are 0. F11 and F22 these are 0. So F11 and F22 if we consider as 0, then the simplified expressions for the enclosure becomes F11 plus F12 plus F13 equals to 1, and since F11 is 0, what we get is F12 plus F13 equals to 1. So from this equation we can directly find out F13. F13 is given as 1 minus F12. So F13 is there. Remember in this equation 19 F13 is there. So this F13 can be replaced as 1 minus F12. Now there is another equation F21 plus F23 equals to 1. Remember here F22 will also be there, but that F22 is equals to 0. So therefore the simplified equation is F21 plus F23 equals to 1. And again in this case we can find out F21. We can find out F21 here. So that becomes 1 minus F23, and F21 then we can convert in the form of F12 by using the reciprocal relation. So the reciprocal relation in this case is going to be what? The reciprocal relation in this case, maybe I just write down. Maybe I will just write down that so that you will be able to understand that in little bit more detail. Let me just add the equation. Okay, so basically F1 in this case, so F21 is given as F21 is given as 1 minus 1 minus F23 so F23 is given by this from 20, and this can further be rearranged as equals to what you are going to get is F21 is given as A2, so this will become A1 by A2 . So this is going to become okay. This is going to be the expression from 20. We can put it F23 in terms of F12. Similarly, we can put F13 in terms of F12, and if you put it in this equation, basically this equation is further simplified as, is it clear to everyone? Is it clear to everyone? If you put it this in this equation 19, so F23 can be, okay, F32 is there, so F32 can be represented in terms of F23. So F23 is given as, maybe I'll just rearrange this part. So F23 in this case is going to be F32 is given as A2 F23, isn't it? So again by reciprocal relation we can replace F32 in terms of F12 directly. So if you put all these things, ultimately equation number 90 is simplified as Q1 is given as sigma T1 raised to power 4 minus T2 raised to power 4 in the bracket A2 minus A1 F12 square divided by A1 plus A2 minus 2A1 F12. Okay. So this is a very important equation. This equation we are going to use regularly. Okay. Is it all right? Equation number 20. Is it clear to everyone what we are doing?
Yes, sir.
Again, similar to this, we can write down equation number T3. Equation number T3 we can directly write down from equation number 18 by replacing F31, F32 and all these shape factors in terms of only F12. Okay, so if we put all the shape factors in terms of only F12, ultimately what we are going to get is equation number 21, which is equation of T3. So equation of T3 is given here in equation number 21. Okay. So can we go to the next slide? Is it clear? This entire analysis, all lot of subscripts are there, but if you do it carefully, then you will understand. There is no mistake in this slide. Please do it carefully. You will understand what we are doing. Okay. So a lot of subscripts are there, and therefore sometimes that connection is missing, isn't it? Sometimes it is not easy to follow, but if you do it yourself line by line carefully, then you will understand what we are doing in this slide. Can we go to the next slide? Hello? Can we go to the next slide?
Yes, it's okay. Yeah.
Okay. Now let's look at the rate of radiation exchange between black bodies. So we are not, see, in the last case we have looked at there is an enclosure. Now we are not looking at enclosure. Okay. So we are just looking at the rate of radiation exchange between black bodies. So consider again two black bodies 1 and 2 of surfaces A1 and A2 with a temperature of T1 and T2 and a total emissive power of EB1 and EB2 respectively. So the rate at which the radiation emitted by a body 1 and is intercepted by and absorbed by body 2 is given as A1 EB1 F12. Similarly, the rate at which the radiation emitted by body 2 and is intercepted by and absorbed by body 1 is given as Q21, that is A2 EB2 F21, and the subtraction of these two is going to be the net radiative heat transfer between these two bodies, isn't it? Correct. So Q12 net is given as A1 EB1 F12 minus A2 EB2 F21, isn't it? Now A2 F21 that we can represent in terms of A1 F12 because that is what the reciprocal relation is, isn't it? Using the reciprocal relation, the surface area multiplied by the corresponding shape factor F12, A1 into F12 is same as A2 F21. So if we replace that, what ultimately we get is A1 F12 EB1 minus A1 F12 EB2. So this A2 F21, this is replaced by A1 F12, and this A1 F12 we can take it common. So what we get is the net radiative heat transfer between body 1 and 2 is given as A1 F12 sigma T1 raised to power 4 minus T2 raised to the power 4. So this is very simple, isn't it? This is very simple. So net radiative heat transfer between two bodies can be given as surface area A1 into corresponding shape factor F12 into sigma and the temperature difference raised to the power T1 raised to the power 4 minus T2 raised to the power 4. Now let us assume that there are n bodies are there. Now there are n bodies are there. So net rate of radiation, so or net rate of radiation energy loss by surface 1 is basically given as summation of this radiation loss with respect to all the bodies including itself. So Qi net, that is the net rate of radiation heat loss by a body 1 by exchanging heat with all n surfaces including itself is given as summation 1 to n Ai Fij. So Fij is nothing but what? The shape factor of surface 1, surface I with respect to surface j. into sigma and in the bracket Ti raised to the power 4 minus Tj raised to the power 4. So this is a generalized expression, expression number 23. Okay, so this expression we are going to use later on when we are going to look at the concept of gray bodies and all. There we are going to look at these in little bit more detail. Just wait. Okay. Is it all right? Is it all right? Can we go ahead?
Yes.
Okay. So now in the radiation, remember, if you look at the radiation, we started with a very simple concept of radiation, that the radiation energy, emissive power, you can directly obtain using Stephen-Boltzmann law, that is sigma into T raised to the power 4. Then we added some more difficulties. We are saying that the radiative heat transfer will not be given directly by the Stephen-Boltzmann law, but there is some more factor is coming into the picture, and that is the directional nature of the radiative heat transfer, and therefore the shape factor is coming into the picture, because not all the radiation emitted by the body will be intercepted by another body, and what solid angle that particular surface is subtending on a given surface, that is important, and that give rise to the surface or shape factor or a component factor or a view factor. Now we are adding one more complication. So far we were only talking about the black bodies, isn't it? So far we were only talking about the black bodies, but the real bodies are not the, these are not as ideal as a black bodies, isn't it? Real bodies are real bodies will not have the emissivity equals to 1, and the emissivity and the absorptivity, this will be a function of temperature and wavelength, isn't it? So even before we go to the real bodies, let us look at something in between the real bodies and the black bodies. So what is something in between the real bodies and the black bodies? Something called as a gray body, isn't it? Real bodies still we will not be able to account in a simple radiation heat transfer equations which we have seen so far, because the emissivity as well as absorptivity, these are also function of temperature, so that adds additional complications in the analysis. But we can analyze gray body. So gray bodies are in between the real bodies and the black bodies. They are not as same as the real bodies, and they are not same as the black bodies, but they are in between. Why I'm saying in between? Because the emissivity and the absorptivity are independent of the wavelength. So we can still do the analysis with respect to the gray bodies, isn't it? In this course, we will not look at the radiation heat transfer using the real bodies. So very often, whenever the radiation heat transfer we are accounting, we in general assume that it's a perfect black body, or at max we can say that it's a gray body. That's it. Not more than that. Is it all right? Is it clear?
Right,
So
sir.
now we are adding one more complication. So we are considering a gray body. A gray body is a body in between real body and the black body. So in a gray body, absorptivity and emissivity are independent of the wavelength. So there is another concept which is a diffused gray surface. So when we are saying a diffused gray surface, what it means is, remember in the earlier slides we have said that diffused surface. So diffused gray surface is the surface if its spectral emissivity epsilon lambda and the absorptivity alpha lambda are independent of the angle of incidence. So whatever the radiations are falling on the surface, the emissions from the surface taking place in all the directions. These are not emitted in one direction, and that is why we are calling it as a diffused spectral emissivity. And similarly, the absorptivity is independent of the angle of incidence. So absorptivity and the emissivity, these are independent of the angle of incidence, and therefore these surfaces are referred as diffused gray surfaces. Okay, so many real surfaces have characteristics close to those diffused gray surfaces. Okay, that is the reason why we are looking at diffused gray surfaces. The another two important concepts which we have to look at Please pay attention. This is very important. These two things are very important because all the slides after this we are going to deal with the gray bodies, and these two things are we are going to use to account the radiative heat transfer. Unlike so far we were dealing only with respect to the emissive power of the black body to account the heat transfer. But now onward we are going to change that to these two factors. These two factors are irradiation and radiosity. So irradiation is the radiation from all sources. Irradiation is the radiation from all sources that hits a surface per unit area per unit time, and the unit is watt per meter square. So unit is same as emissive power, but it is denoted by G, capital G. It is denoted by capital G.
Hello, sir.
Yes. Hello. Yeah.
Sir, can we please stop here, because if these topics are very important, I think we should take them in the next.
I will stop at this slide. Yes, I will not go ahead of this.
Right,
so I'm only giving the brief background about the terms, and we will continue from these terms in the next class.
All
okay.
Right.
I'm not continuing from this point onward. Yeah. Okay. So another concept is a radiosity. So radiosity is the total radiation that leaves the surface by means of emission as well as by means of reflection. And again, total radiation that leaves the surface per unit area and per unit time. So the unit is same as watt per meter square. So unit is same as the emissive power, but it is denoted by J, capital J. So when we look at the radiosity is nothing but what? The radiation emitted plus radiation reflected. So it accounts both reflection as well as emission, isn't it? So this is nothing but what? This is nothing but what? EB plus reflection, isn't it? Reflectivity multiplied by the incident radiation. Okay. So here you can see, if you look at the perfect black body has radiosity same as EB. Radiosity J is same as EB because perfect black body do not reflect anything. Whatever the incident radiation falling on the black body, everything is absorbed, isn't it? So there is no reflection. So in case of a perfect black body, radiosity is same as emissive power EB, capital EB. Is it clear to everybody? Is it clear? Hello?
Yes, sir.
So we stop here. We will continue from this point onward in the next class. Okay?
Yes, sir.
So today the lecture was audible and everything was all right. So we should continue in this way, is it?
Definitely, sir.
Okay, I am really sorry because last 2-3 lectures really messed up because of this internet and other things. I myself generally go through the recorded video, and I could see that the videos were not very clear at some locations. Some delay was there in some locations because of internet issue. Things were not clear. I'm really sorry because whenever I am on the slide, I don't get to know these are whether these things are going in a right direction or not. I don't get to know whether the internet connectivity is good or not. That I don't get to know. So that is why I thought today I will continue in my office just to check whether the internet connection is good here. Okay, all right. So we stop here. We will have a tutorial for both the batches today. So now onwards, as I said in the last class itself, the tutorials we are going to have only on Monday. Okay, so no tutorial on Tuesday because the attendance was very less, and we are continuing the same thing. Anyway, the lectures are available in a recorded mode, so it is better to do it on Monday itself. Is it all right?
Yes, sir.
And all tutorials are already uploaded on a MS Team, so you can have a look at it. So probably we will cover 2 tutorials, 9 and 10 today. Okay. Okay, all right. So we stop here. Please stay safe at your place. Things are messing up big time.
You too, sir.